Okay, this is the third lesson. I think the microphone of one of you is on. I can hear some noise. And so I'm. This is the third lesson for our Python course. And first, I will give you the solution for the exercise that I gave in the second lesson. And then I will talk about comprehensions. The next thing that I will talk about is Numpy. Numpy is a big library that is commonly used with Python. Actually, the plan was not to give Numpy in this lesson. I wanted to give Numpy in the last lessons if we have enough time. But I thought it's not a library that's just for fancy thing. It's used in most applications, the most source codes that you download from the internet. So it's good to learn Numpy. It's not part of the standard Python. So in this lesson, we will talk about Numpy. We will not be able to cover all the topics that exist in Numpy, but we will talk about the most fundamental things. Probably we will spend some time. We will allocate some time of the next lesson also to the to Numpy, but the most fundamental and important topics we will cover today. So we will talk about NDARRAYs, array creation routines, array scalars, data type objects, and I will talk about some topics through some examples. Array creations, slicing, advanced indexing, copies and views, reshape, in-dime and A-range, traversing over NDARRAYs, and broadcasting will be discussed today through some examples. So first, the exercise that I gave you last week was this one. Given the following list, we want to record all the position in a list where the value is none. The value is none, not this one. The value here is a string, but this one is the value of none. So using these examples, I wanted you to get familiar with this value and also how to record the positions of some items in a list. So the solution is this one. First, I created a list, which is the given list. And then I gave you here 3 different ways to do this exercise. So the first way is similar to what we have in other languages, like C++. So the way that I'm solving the solution, the exercise, solving the exercise here, is not a way that is very common in Python. It's more mimicking the way that we solve an exercise in solving such an exercise in C++ or other languages. So here I have a list which will include all the indexes of this non-value in this list. Then here I'm creating an iterable. You are familiar with iterables in because we discussed about them in the last lesson, in the second lesson. And to create a range with this list, I'm getting the len of this list, which is 8, because it has 8 elements. And with range, if I put 8 here, it gives me a list. It's not a list, it's a range which produces the values from 0 till 7. So with this 4, I will traverse over the values from 0, integer values from 0 till 7. And then through that iterator, I will check every item of this list to I will compare them with none. If it is none, we are familiar with if structure. If it is none, then I will append the index of that one to this list. And after that, I will print this list index, this list. So it will gives me this list because the position of this none and this none is 1 and 3. We know that it starts from 0 here. So in this solution, we had to iterate over a range of indexes. This one, which is very similar also to other languages, but I think this one at least is somewhat more similar to Python codes than this one. In all of them are Python codes, but the style of programming is different. So the style of programming in Python is different from the style of programming in C++. So you can write a code in Python, but with different style. So in here, I mean, in this solution, again, I have a list. I have an iterator. So I'm updating the iterator by myself. Here, I didn't update the iterator because I had a range of the iterator values, and I could iterate over those values. But here, I'm iterating over the items of this list because I'm iterating here in a list, and I'm updating an iterator for myself by this one. Item is none, and now I'm if item is now, I'm adding this I to my list, and then I update that with this one. Again, I think this one is a bit cleaner than this one. But what is similar, what is really Python style programming? This one, we are familiar with enumerate, we are familiar with unpacking. So I'm enumerate over this list, and enumerate gives me the index of that item and also that item. So it gives me a tuple of the index and the item itself. So with this one, I and item, with I have the index of the items, and with item I have the items. So I only check the item with none, and if it is none, I will compare that. If it is none, then I append I to this. Then I print that. So you can see with these 3 different solutions, I'm solving this exercise, and all of them are creating the same list but with 3 different style of programming. Today we will talk about Numpy. In Numpy, and there I will also solve this exercise with Numpy, and you will see that with Numpy you can do it in 1 line of code. So even using Numpy makes it better. So the other topic that we should talk about, that is comprehensions. But before that, I don't know who's let me see. Both of you are muted, but I don't know why I hear some noise. Okay. Okay, comprehensions. Maybe I should. Okay. It's better. Can any one of you talk now on mute? Because reduce the volume of my PC, and I'm not sure if later on I can hear you.
Hello.
Okay, so I can hear you well. Thanks.
Okay. You're welcome.
Okay, but the noise has been removed. Okay, with comprehensions, this topic is also related to iterables that we discussed in the last week. We can use comprehension for different types of iterables, but we start to talk about that with list. So in this slide, I'm talking about list comprehensions. These are unique to Python, and we don't have them in other languages. At least to my knowledge, we don't have it in other languages. List comprehensions provide a concise way to create lists because it's list comprehension. But if it was DICT comprehension, it was a way to create DICTs. List comprehensions make new lists. Each element is the result of some operations applied to each member of another sequence or iterable. We will see in the exercise, in these examples, what does it mean. It creates a subsequence of those elements that satisfy a certain conditions. So these are two applications of comprehensions. Technically, a list comprehensions consists of brackets. This is a list comprehension. Consists of brackets containing an expression. This is an expression followed by a for clause. This is a for clause. Then zero or more for or if clauses. Zero or more if clauses here. So here it's zero. But at least it has an expression and a for clause inside a bracket. Because it's a list. If it was, for example, sets, then you will see here braces. So this is the definition for a list comprehension. The results will be a new list resulting from evaluating the expression in the context of for and if clauses which follow it. So here we don't have if, but you will see in the next exercises how they work. Let's check this one. I'm going to create a list, and every item of the list is a square of its position. 0, 1, the position here is 2, a square of 2 is 4, and 3, the square of 3 is 9, and the rest. So how can I generate that without list comprehensions? So I can generate an iterable, which is range of 10, which gives us the value between 0 till 9, and I will iterate over that, and I will append the square of this, every element, to this list. And when I print the squares, it gives me this one. But X is still existing after this loop. So it's not similar to other languages. If you have a for with some variables inside that, it's not local to for. It can be used after the for block. You can have access to that here. You can delete it here by yourself, or you can put it like that and don't use del, and the garbage collector will delete that one later on based on its rules. The other way, instead of this one, to generate this list is to use this syntax. You're not familiar with lambda functions now, but we will discuss that probably in the next lesson about we'll discuss that about lambda functions. But just to all of them together in these examples, I also talk about this one. Lambda is a function, and like this, it has an input and it has a body like this. And map is a function that returns a map object, which is an iterator, of the results after applying the given function to each item of a given iterable. So map has a function as the input and an iterable as the also as an input. So it will apply this function to every item of this iterable and keep the results together in one map object. We can convert that to a list, and then it will be this one. So here, for every item of this range, I will apply this function. The input is, for example, 0 squares 2, again 0. And then I will convert all of the results to a list object, and it gives me this one. So it's somewhat better than this. It's in one line of code. This one, before this one, you have to have 3 lines of code. But it might not be very clear, very readable for people, so we can use list comprehensions instead. And especially for when we have nested fors, this way is very difficult to be used. With list comprehensions, I have an expression. The expression is like the body of the function that we have in Lambda, the body of our loop that we had here. And for every item of this range, I'm going to apply this expression, and it will be one element of the list, the resulting list. And you can see here the squares will be like this. So this is 3 different ways that we can generate one list, but this one is the best solution for this example. Okay, we said that comprehensions can be used for different iterables. We saw an example with list. Let's see the examples in different for different iterables. The first one here is still a list, but we have a nested loop. What does it mean? I didn't talk about nested loops. I assume that you are familiar with that, but with this example, I wanted to give you some information about that. With this one, this is a for loop, which is iterating over a list with these items. The body of a loop, this loop, is again another loop. So for every elements of this list, for every run of this for, we will run another for. We will have another for. And for inside this for, I'm iterating over again this list, and I'm checking, I'm comparing the items of this list with this one. And if they are not the same, we will create a tuple with X and Y and append it to another list. The results would be like this if we run the whole loop. So 1, 3, 1, 4, because 1, 1, they are equal to each other. So we don't have 1, 1 here. Okay, let's see how can we do this using a list comprehensions. So we said that in list comprehensions, we have X and Y, we have an expression. I can hear some noise again. Rayhane, could you please mute your microphone? Thanks. And okay, we will solving the same problem with list comprehensions. We said that for list comprehensions, we have an expression, and then we have some a for clause and 0 or more for and if clause. So with this for, it's similar to this outer for, and this for is similar to this for, and this if is similar to this if. But all of them is one line of code, and also X and Y does not exist after this comment. They are local to these brackets. So if I print comes here, you see that this is the same as this one. Sometimes we may need to have a set of these tuples. I can convert a list to a set with this function. Also, I can convert that to a tuple. I can convert that to a DICT. But as you can see, the result is different, because with DICT, we have key and value. If we consider the first elements of the list as the key and the second element of the this tuple as the value. But as we said in the I think in the second lesson, DICT keys cannot be duplicate of each other, and the last value will be considered as the final value. So 1, 3, 1, 4. So 4 will be considered as a value of this DICT. Okay, here I wanted to also make you familiar with converting these iterables to each other and the resulting results of the converting process. But we can have sets and tuple and DICT and str comprehensions as well. We don't need to use list to generate a set, because here you are creating first list and then convert it to a set. So this is a set comprehension. This is very similar to this one. Here it could be a set or it could be a list. So any iterable that is, it can be used here because it's a for, and for is iterating over iterables. And the results is a set because I'm using braces here. For tuple, I'm using tuple here and with this one. And again, it's very similar. It could be here again a tuple or other iterables. With DICT, the expression is somewhat different. I'm using X colon Y to create a DICT, and the results again is similar to what we had by converting the list that we had from list comprehensions. What about STRs? For STRs, let's first see this example. I want to iterate another list from, another string from this one just by iterating over the items of the list, the string. And with this one, I can do that, but I need also a join function to join all the strings resulting from these four. Here, this is the delimiter that I'm using to join all the strings, resulting strings that I have with this string comprehensions. I mean, the delimiter that I have is an empty string. But if I put here just a character, which is a space, Then between every item of this one, I will had a space. You remember this one? If I don't use my mouse, you will see that the code, the command in the line 32, you are familiar with that because we had it in one of our exercises in the previous lessons. Sorry. And with that one, we could print, we could generate another string and whose strings are the reverse of the input strings. But we can also do that with list comprehensions, with strings comprehensions. And how can we do that with this one? This range gives me, I'm saying that you should give me a range from the end of the list to the beginning of the list, and the step of that, when I said it was a mistake that I said list. It's not a list, it's a string, but they are sequence data type, they are very similar, so they can be used very similarly. So with range, I'm creating a range of values, and with this range, I'm saying that it should be a start from the end of the string till the beginning of that, and it should be traversed in the reverse order because the step is -1. And with this command, okay, I should not move my mouse because otherwise you cannot see it clearly. With the code in the line 31, you are iterating over that range, and for every value of that range, you are returning the string, the character in that position from the string variable s. So sx gives me the character in the position of x, and I'm joining them with the empty string. And if I print that, I will see this one here. But I should confess here that the code in the line 32 is better than 31. You can see that it's very short and much more readable. So as you can see, when we are learning about Python, we see that we have many different ways to deal with the problem, but every time we should find the best way to solve our problem. So you may think that, okay, comprehensions are very advanced tools for us to solve a problem, so we can always use that because it's very advanced, but no, it's not correct. For every problem that you have, you should see which one is the best way to go for it. So for such an example, slicing is a better option than comprehensions. Let's see here DICT comprehensions. With the DICT comprehensions, you just saw that the example, but the style is like this: the expression is key and value for every item in the in this dictionary.items gives us the items of the dictionary. If you remember from the last lesson, we said that if you want to go through the items of a dictionary, we should use this method, and by this one we are unpacking the items to a tuple of key and value. So we have a DICT here. This is key and this is value, and with this one, this is a DICT comprehension. I'm doubling the grades of each one, the value of this dictionary, and creating another list. So it's very fast and I can do it with comprehensions. Let's see this example. I have a dictionary like this. This is temperature 1, temperature 2, and so on. And this one is the values are in Fahrenheit. I want to make it in Celsius. So one of the solutions is to use lambda function and the map, the one that we just talked about that in the previous slides. How? We have a lambda function here, and we have our iterables, which is here is the values, because we only want to change the value of this dictionary. And for every item of this iterable, I'm applying this function. The results will be concatenated together in a map object, and that map object will be converted to a list. Now I have the list of values in Celsius, but now I want to create a dictionary from the keys and the values. So the values is here. The keys of the Fahrenheit can be accessed via this. With zip, I can concatenate them together in one object, and then by DICT, I can convert that zip object to a dictionary. And when I print this one, it gives me this. But you see that 1, 2, 3. 3 lines of code is needed to generate that dictionary, to do this process. But I could do this one with this line of code with DICT comprehensions. How? I have again K, the structure was key, value, and the 4. Key is here because I'm iterating over the items of the DICT. It gives, I'm unpacking that to K and V. K here is the key. I want to have the same key in the resulting dictionary. I could also change the keys here. And the value is the body of the same function. So with this body, I'm changing the value from Fahrenheit to Celsius. And if I print this one, it gives me again the same dictionary. So in this scenario, using a DICT comprehension is better than using this solution with lambda and the rest. But it doesn't mean that lambda functions are not good. In other scenarios, lambda function might be a better option than DICT comprehensions. Okay, before going to Numpy, talking about Numpy, is there any questions about comprehensions and the rest of the things? No problem, Rihanna. Did you get list comprehensions? Okay, very good. If you have any question, you can ask. Okay, let's go to the Numpy library. Probably you have heard about that before, but it's a big library that is commonly used with Python, but it's not part of a standard Python programming language. But it's very commonly used. So every source code that you download from the internet, you will see that they are using Numpy. I can say 99% of the time you will see Numpy in the codes that is written in Python. So that's why I'm talking Numpy here, because you now are familiar with the built-in data types in Python. But so it's good to get familiar with Numpy, the data type that it provides, and the functions. We cannot cover the functions, all the functions sorting functions, searching functions that we have in Numpy in this lesson. We will talk about that in the next lesson. But the most fundamental topics we will discuss today in this lesson. So let's have a recap on the list. We know that list is a collection of values. List holds different data types. We can change, add, and remove the elements of a list. But what is missing in lists? Mathematical operations over collections and their speed. We will see what does it mean when I say that mathematical operation over collection is missing in lists in this example. But when analyzing data, you often want to carry out operations over entire collection of values. But this is missing in lists. Let's see here. We have two different arrays, weights and heights. And we want to compute the BMI for these weights and heights. I can compute the BMI for every element of this list by this expression. So for example, for the first elements of this list, I can do this operation to be able to compute the BMI. But I cannot do this one. I cannot do this mathematical operation over the whole list. This one, if I do this one, I will get type error, which is written unsupported operand types for this one or pause list and ints, because I'm doing the mathematical operation between the list and between the list and init, an integer. But this is possible in Numpy with Numpy arrays. But if I don't have Numpy, how should I solve it in Python? I can do this with a for loop. I'm zipping weight and height and unpacking that weight and height and do this mathematical operation for the scalar values for these floating point numbers one by one and append it to a list to generate the list containing all the BMIs for every items of this list. If I print this one, I have this list. But it would be very great if I could have this way of solving this mathematical operations over the collection. But in list, it is not possible. We will, okay, let's talk about what is Numpy, and then we will come back to this example. Numpy is an abbreviation of numeric Python, so num and py. The core library for scientific computing in Python is Numpy. So if you want to be a data scientist, you will use Numpy for sure. Numpy gives us Numpy array, which is an alternative to Python lists. It lets us to do the calculation over entire arrays. It's easy, it's fast, and we will in the next exercise we will see why it is fast. With Numpy, we can do mathematical and logical operations on arrays. We can do Fourier transforms and routines for shape manipulations. We can do operations related to linear algebra. Numpy has built-in functions for linear algebra and random number generations. I'm not sure we can discuss about all these topics in these lessons, but in this course, I mean. But if you learn the fundamental concepts in Numpy, you will be able to learn these things by yourself. Numpy is often used along with packages like SciPy and Matplotlib. These two are a replacement for MATLAB. because in MATLAB you have a popular platform for technical computing. You can plot what your diagrams, you can do some operations over the matrices, but if you want to have them also in Python, you should use SciPy and Matplotlib. But these are the packages that are using Numpy as well. I know I've heard from some of my friends that are listening to this course that they are really willing to learn SciPy and Matplotlib. But I already told them that you can learn them if you learn the fundamental topics in Python and Numpy. You can easily work with any other libraries because you know the basic things base of this language. So then working with other libraries would be very easier for you. I mean, as a programmer, you don't need to know all the libraries. You only need to know what a language is. For example, when I talk about C++, I know C++. Then as a programmer, I should be able to work with OpenCV or work with Qt library. I mean, for me, it should not take much time to get familiar with other libraries because I know the language itself. This is also the case with Python. When you know Python and Numpy, it should be easy for you to get familiar with other libraries like SciPy and Matplotlib. Numpy is open source. You can get Numpy, the source code of Numpy here. Since it is not part of the Python standard program, I mean the standard part of Python language, you have to install Numpy for your PC if you want to use Numpy. You can also use some online interpreter that Numpy is already installed in them. I can send you back some online interpreter, the address of some online interpreter later. But if you want to install Numpy on your PC, you need to go to your command prompt and run this line of code, pipe3 install Numpy, because I assume that you have Python 3 on your PC. So with this one, you can easily install Numpy on your PC. Most of the parts that require fast computations are written in C and wrapped in Python for ease of use. So we said that Numpy is faster than Python list and Python fundamental data types, fundamental containers data types, because most of the methods of its data types are written in C, and they are really optimized and they are faster than the other data types that we have in Python. I mean, they are faster than built-in data type in Python. Why is Numpy faster than lists? Numpy arrays are stored at one continuous place in memory, unlike lists, so processes can access and manipulate them very efficiently. If you remember from, I think in the second lesson, I told you when I was giving the advantages and disadvantages of mutable and immutable objects, I told you that we can access immutable objects faster than mutable objects. And when I was saying the reason behind this, I told you that immutable objects are in one location of memory. When we create an immutable object like tuples, we get one location of one continuous location of memory for ourselves. We reserve that, and if we update that, since we cannot update immutable objects, another location of memory will be reserved for us, and a copy will be done there. So we said that we can access immutable objects faster than mutable, but updating them is expensive than mutable objects, because when we update immutable objects, we only need to update one element, not the whole object. If you remember, lists are mutable objects. So here with Numpy, we are saying that Numpy arrays are stored in one continuous place of memory. So they are similar, the way that they store in memory are similar to immutable objects, but they are not immutable objects. We can say that they are a combination of immutable objects and mutable objects. That's why they are faster. We can access them faster than lists, because lists are mutable objects and they are not stored in the same location of memory. I mean, the items are not next to each other. If we want to see how a Numpy array memory and how Python lists are stored in the memory, we can look at this figure. In Numpy array, all the items of the array have the same type. Unlike the list that we said that every elements of the array, every elements of the list can have different types. So for Numpy arrays, we only need to store the type of the array once, because every elements of the array has the same type. So we only need to store that. The type of the elements is, for example, a string, and it will take 8 location of the memory, 8 bytes, for example. So we don't need to store this one for every element. But for Python lists, we have, first of all, they are not located in the same location of memory, as you can see. For example, the first element is here. The second element is here. The third element is here. This element is here. So every item is in different location of memory, depending on the situations that we have in the memory. So depending what other variables, where other variables are located in the memories, they find the location for the list. So for every time that we are adding an item to a list, another location of the memory will be reserved. But for every item of the list, we have to store the type of that item and the amount of memory that it needs. As you can see, for example, here, this is the item, this is the type of the item. But for Numpy array, we don't need to do that, because every item has the same type as the other items have. But as I explained here, in a special case that all variables are the same type, I'm talking about the lists here. Much of this information is redundant. It can be much more efficient to store data in a fixed type array. So even if you have a list of integers, since list by its nature, a list by its nature can have different types for different items, it has to store the type of that item, every item next to that item, even if all the items are in the same, are having the same type of value. So we will have much redundant, but this is not the case with Numpy arrays. So the very common data type that you will use more often in Numpy is NDARRAY. What is an NDARRAY? It's an n-dimensional array type. It's a collection of items of the same type. We just said that, we just saw that. Each element in NDARRAY is an object of data type object called dtype. In the next slide, we will see what a dtype is. But for now, we should know that dtype lets us know how each item in the array is to be interpreted. A dtype can be basic types, like we had integer, float, or the other things, or it can be a data structure. With data structures, we can have the items in the NDARRAY that apparently are different from each other. The type of them are different from each other, but in fact they are not. They are, we will see in the exercise. I think here without exercise, without examples, it's not really clear. But you should know that every item of the NDARRAY has a dtype, and it lets us, it lets the interpreter, the Python interpreter, to know how to interpret every element of the array. The common way to create an NDARRAY is this one, is this constructor, this function from the Numpy array. It receives an object which is an iterable. We are familiar with iterables. It can be also another Numpy array. The type, by default, the type is none, and none can be converted to float. We will see in the next slides. With copy, it says that if we should copy the items of object to the resulting object, which is by default true, or if I put false here, then the object will not be copied. The resulting object, the resultant object, will be a reference to this one. I guess it would be a view, but you can check yourself if it will be a view or it would be a reference. I think I didn't check this one in the examples. But if you do it yourself, you will learn more, but I guess I will do it in the next lesson. And the order tells us how to tells the interpreter how to store the elements of the array row-wise or column-wise. I think I didn't. Yeah, I didn't explain this one in the next slides. But arrays can be, for example, we can have an array 2 by 2, which has 2 rows and 2 columns, and then I can store it. Since I said that in this example, that all the elements of the array will be stored in one continuous place of memory. So then you cannot store them like a matrix. You will store them row by row or column by column. So if it is row by row, let's see if I have an example here. An example of I have to go to this. Oh, okay. For example, this is this one. This is an array, an NDARRAY, which has 3 different rows and 2 columns. So it is 3 by 2. And how this one will be stored in the memory if it is row by row. So first this one, second this one, third this one, fourth this one. So this is the way that you will store this one in the memory. But if it is column wise, then this one, this one, this one, and then this. So first to, this is the way. Okay, I should have put one example in this slide, but I forgot. Yeah, here. So the order is defined how you will store your array in the memory, row-wise or column-wise. What is sub OK? By default, it is false, and it says that if the resulting array will be an instance of a child of this object or not. You are not familiar with inheritance, but you will be familiar with that in the next lessons. If we have inheritance, with sub OK, if I put true, then the resulting object will be a child of this one, but by default it's false. So when you create an array from another array, the resulting array is a base class. It's not an inherited class. And NDMin is the minimum dimensions of the resultant array. Imagine you have an object here which has the shape of 4 by 5. So this object has 2 dimensions. Every dimension, I said that this object the shape of this object is 4 by 5. So it has 2 dimensions. The elements, the number of elements in the first dimension is 4, in the second dimension is 5. If I put here NDMin to 3, then I'm saying that even if the object has 2 dimensions, I want to resulting array has 3 dimensions. So 3 dimensions. So the broadcasting will happen, or this function will broadcast, will extend the array to an array that can have this, that can meet this in this minimum dimension that we set here. For example, if you put here for one element, one integer value, and if you put here 2, then it will have, I hope I give you one example here. I'm not sure if you are getting that very well or not, but I think in the examples I have such an example. If you put, for example, a list here, if I put a list with this one, and inside that with 2 brackets, and inside that I have I have 5. I mean 5, the value of the item of that list is 5. Then if I put here 2, the resulting array would have 2 brackets. Instead of 1 bracket, it will have 2 brackets because it should have 2 dimensions. Let's see if I give you that example or not. If I didn't provide you this example, I will provide this example in the next lesson. So array creations routines are this one. Actually, there are more than the ways that you can see here. You can go to this address to see the other ways to create arrays, Numpy arrays. But the most common one are this one, empty ones and zeros. With this one, you can create a Numpy array with this shape, and the items of this this array, the resultant array will not be initialized without initializing the entries. And with ones, it's similar to this one, but the items will be filled by 1. And with zeros, again, similar to this one, but the items will be initialized by 0. And empty like, ones like, zeros likes, it's with these ones you can give an object in the input of this as an input to these functions, but it will use the shape of this object, not the values, the shape of this object to create another NDARRAY. So This the resulting NDARRAY from ones like has the shape of A, but the values would be 1. You can also define the other value, the other options that you have. You can change the dtype, you can change the order subbucket, and the rest that you have in function numpy.array. So, and full, you can also define with which value you want to fill this the resultant array. So the shape is this one, but instead of 1 or 0 or not initializing anything, you can put here, for example, 2. So if you put, for example, here a shape of 2 by 2 and put 2 here, then the resultant array would be an array of the shape of 2 by 2, and the value would be the value of the items also would be 2. Okay, before creating array, let's see what array scalars and dtype objects are. I hope you understand till now what an NDARRAY is. Theoretically, I know you should see some examples to understand them better, but theoretically, I think you understand how they are stored in the memory and how we can create an NDARRAY. Again, theoretically, you should see them in example. If there is any question, you can ask. Otherwise, we can go to other topics. Is it clear? Not 100%, but 80%. Is it clear?
Yeah, it's clear for me.
Okay. Let's. We should see some examples. I know it's not really clear till now because we just talk about them theoretically. But before creating arrays, we should know what array scalars are and what dtype objects are. So before knowing them, it may bring us some ambiguity for you when we are creating arrays. So the first things, what array scalars are. Array scalars are different from the scalars that we have in Python. It's an item extracted from an array by indexing, not slicing. So if we index, for example, if I extract one item from an NDARRAY, that item is an array scalar. The primary advantage of using array scalar is that they preserve the array type. They have identical behavior between arrays. They have identical behavior as the arrays. So we have arrays and scalars. They have similar methods and they can work similarly irrespective of whether the value inside is an array or not. So that's why we have array scalar. Even the item is an integer, but it's an array scalar since it's an item of that NDARRAY. And we can treat them similarly, treat arrays and array scalars similarly. Python defines only one type of a particular data class. There is only one integer type, one floating type, and so on. This is good. I mean, in the first lesson, when we were discussing about Python and Python data type, we said that the reason behind this is that they want to make the programming easy and convenient for the programmer. So that's why we only have one integer type. So they want the interpreter take care of the memory and the rest of the things. But for scientific computing, more control is often needed. The interpreter itself cannot go for the best options that you have. So you have to intervene. In that case, we have to use Numpy. Numpy has 24 new fundamental data types to describe different types of scalars. These type descriptors are mostly based on the types available in the C language that Python interpreter is written in. We can have different Python interpreter. There are different Python interpreters. Some of them are written in C, some of them are written in Java, and the rest. But Numpy, since itself is most of it, the parts of Numpy is developed in C, so we are using C Python. C Python is just a Python interpreter, and the type are provided that the types that are Numpy are the ones that are similarly to the ones that are available in C language, and there are some other additional types which are compatible with Python built-in types. Formally speaking, array scalars are any object which is an instance of Numpy generic or whose type is Numpy scalar type. So this is the hierarchy of array scalars. All of them are getting inherited from generic, Numpy generic. It's a class defined in Numpy. And to check if an item is, if a value is a scalar or not, we have two ways. We have a function numpy.isScalar val, and it tests that if it is a scalar or not, or we can check that with this function if this value is an instance of generic, because we know that every Numpy scalar is a child of this class, the generic class. So we have two ways to do this. And something that I'm using here in NP. This is really a name that many people are using for NumPy, but in fact, this is not a term that is defined in the interpreter or in the NumPy. So we will see later how we can name a library when we are importing them. So this is NP is a name that I set when I was importing NumPy library. So it's not something that is defined by default in the interpreter, but it's a name that most programmers are using for NumPy. Built-in scalar types. The default data type in NumPy is float. So if you don't set a data type, and if you don't have also an object, because you saw that when we were creating an NDARRAY, we could use NumPy array and an object. If we don't have even that object and we only give shape like numpy.zeros, not zeros, numpy.empty. So, and if I don't define the D type, if I don't define any object, then the default data type is float. Otherwise, it will extract it from D type, or it will extract it from the type of the object that you are sending to your numpy.array function. Some of the scalar type are essentially equivalent to fundamental Python types and therefore inherit from them as well as from the generic array scalar type. So we said that all the array scalar types are, sorry, I need to see the time. We said that all the array scalars are getting inherited from the generic class, which is a class in Numpy. But for some of them, they are equivalent to fundamental Python type. So they are getting inherited from those fundamental data type as well. Which are they? Int, float, complex, byte. These are the scalar type, and the equivalent Python type are these ones. These are the built-in scalar types in Numpy. We said that we have many different data types, and if you are familiar with C++, you may find them very similar to the way that to the data types that we have in C++ and C. So these are the data types. We have multiple ways to define integer, multiple ways to define floating point numbers, and also we have any Python object, which is here. You will see one example with this one to see if we convert a list which has elements of different data types to an NDARRAY, then you will see that the resulting array will be of type object. We will see that, but keep this in your mind that we have a data type, a scalar data type, array scalar types, that is object, and it can be any Python object. Array scalars has some attributes and some methods. Since they are getting inherited from a generic class, so they have the function that is provided by generic function. We cannot talk about all the functions, all the attributes in this course, but we will discuss some of them, and you can learn them by yourself if you want. But for example, shape is a tuple of array dimensions, and dim is the number of array dimensions. And for example, items is the length of one element in bytes. Real and imaginary part of the scalar, and the rest of the things that you can see here. Yeah, array scalar, as I said previously, has the same attributes and methods as array. So that's why we have array scalar, in fact. Method of scalar types, again, we have these methods, and the default behavior of this method is that they will internally convert the scalar to an equivalent zero-dimensional array and to call the corresponding array method. You don't know what is happening. You just call those methods from the array scalars and from the NDARRAY, and you think that both of the methods are working the same. But in fact, the methods of array scalars will internally convert that scalar to an array, and they will call the method from the NDARRAYs. Okay, we have learned what array scalars are and what scalar types are. Now let's see what a dtype object is. If we learn dtype object, then we will be ready to create NDARRAYs. I hope you are not tired, but we have to go through this theoretical aspects to be able to go to the examples. We will have many examples in the next slides, oh, I think I forgot to record the meeting. Did I record the meeting? Yeah, I'm recording, sorry. I just remembered something. Okay. We have you will see many examples in this in the other slides, and but to see those examples, you have to know what scalar types are and what dtype object is. So we have to first learn them theoretically and then go to the examples. But don't be tired. I need to have you for the examples. D-type objects. We said that arrays are a collection of items, and every item have the same type, and the type is a D-type object. What is a D-type object? A data type object, which is an instance of the class Numpy, the dtype, describes how the bytes in the fixed size block of memory corresponding to an array item should be interpreted. And it describes the following these aspects of the data. So it defines the type of the data, for example, if it is integer, float, Python object, and so forth. It defines the size of the data, how many bytes we need for that integer. The byte order of the data, little endian or big endian. If you want to know much more about this little endian and big endian, just Google them and learn more. But in this course, we cannot cover that. But just for the sake of curiosity, little endian and big endian, the way that we will store an item, a data in the memory. In some machines, they are little endian, some machines are big endian. So in big endian, the most important byte will be stored in the first location of the memory. I mean, if we have, for example, 4 bytes for our data, that 4 bytes, the most important byte will be saved in the first byte, and the order is like that. And in the little endian, the least important byte will be stored in the first location of memory. But this is important to be considered when you are creating, for example, you are storing one binary file in one machine, and with little endian, because that machine is using the little endian way of the default way of storing data. The default order is little endian in that machine. And now you want to read that file in another machine that is using big endian order for reading the files. Then you have to be really careful with these things. But if you are generating and reading the data in one machine, or in the machines that they have the same order, then you don't need to care about these things. The other things that a D-type object defines is this one. We said that data type can be a basic types in when I was introducing NDARRAY, I said that we have D-type and they can be either basic types or a data structure. So if D-type is a data structure, and which is an aggregate of data types, 3 different things will be defined by D-type. What are the name of the fields of the structure, and what is the data type of each field, and which parts of the memory block each field takes. Data structure have some fields if you are familiar with a struct in C++, you know that a struct has some fields and some values. They are similar to the classes, but they are not classes. Data structure here in Numpy is also similar to that. We have some fields and some values. And if we create an array of a data structure, every item of that array will be a data structure. And that data structure may include different data types, even may include subarrays. So this is the way that we can have different data types in one NumPy array. We will see in the example how we can generate them and how to manipulate them. And if data type is a subarray, what is its shape and data type? You should know that the scalar data types that we just discussed about them, the 24 data types that I showed you in one slide, in the previous slide, are not dtype objects. They are not an instance of dtype class, even though they can be used in place of one whenever a data type specification is needed in NumPy. We can use them instead of dtype objects, but they are not dtype objects. Whenever a data type is required in NumPy function or a method, either a dtype object or something that can be converted to one can be supplied. And these conversion can be done by dtype constructor. So scalar types can be converted to dtype objects, even without this. In most of the methods and functions of NumPy, even you don't need to put this constructor when you are using scalar types, because it will be implicitly converted to a dtype object. But you should know that they are not dtype objects. The question is, what can be converted to a data type object? A dtype object, it is obvious, a dtype object can be converted to another dtype object. None, which which is similar to having float, to write float there, because we know that the default data type in NumPy is float. Array, scalar, and generic types, built-in Python types, so dtype, and the rest. I will go through one by one in the next slide, so that's why I don't read all of them here for you. So array scalar types, we said that this one is not a dtype object, but it can be converted to a dtype object by this constructor. Generic types, we have these generic types in Python, which can be converted to a dtype object, float, cfloat, int. Built-in Python types, float, complex, bytes, str, and the rest that we have in Python can be converted to dtype objects. The types that you will any type that has a method which is called .dtype. So you can get inherited from a dtype class, and you can implement that function by yourself. So this is also possible. We have one character strings. If you remember, let me show that again to you here. For every type that we have a name here. We had also a character code. So for integer, for example, we have I here. For float, we have F. For strings are not here, are not written ever, but strings are U, for example. So here I can convert this one, for example, this one is a double precision floating point number, which can be converted to a dtype. And this is the way that we can do this one. Each built-in data type has a character code. I just mentioned that, and uniquely identifies it. And this is the way that you can say that it's big endian, little endian, or hardware native. I mean the default of the machine, and it defines the byte order. So I could put here, for example, this big endian or equals or the other things to define how I want to store one item. The other one is this one, array protocol type strings. The first character here, it specifies the kind of the data, and the remaining character specifies the number of bytes per item. So here, for example, I'm creating a data type f, which is a float 8. I'm saying that 8 bytes should be reserved for an item of this data type, which is 64-bit. But if since it is a float, this one is the number of bytes. But if it was Unicode string, so except for Unicode, the number here will be interpreted as the number of character of that string. So if I put here U or A even, I think, if I put 8 after that, it means that we have a string. I mean, if we define an item of this type, that item can have at most can be a string which has at most 8 characters. But if I put, like the example that you can see here, F8, it means that if I have an item of this type, it would be a float, and it will be stored in, I mean, for that item, we have to reserve 8 bytes of memory. The other way to define a dtype object is this one. In this way, with this way, I'm creating a structured data type, a string with comma-separated field, like this one. A shorthand notation for specifying the format of a structured data type is a comma-separated strings of basic formats. So you see here, this is comma-separator. I'm saying that I have 3 different fields. Every item which is separated with a comma is a field. And the name of these fields is this one, from 0 till n-1, F0, F1, F2. So we will have a data structure which has 3 different fields. The name of each field is F0 till F2. But what are the type of each field? The first field is a 3-character string. This is 3, and this is A, which is a unique code for a string. F1, it contains a 64 unsigned integer, which is not a capital letter, is a Unicode for unsigned integer. I'm saying that I want to have a subarray with the shape of 3, because here is the shape, here is the bytes, and I want to reserve 8 bytes for every item of this subarray. The shape of that, so it would be a subarray with 3 items. Every item contains a 64-bit unsigned integer. What is the third field? The third field is a subarray with the shape of 3 by 4 containing a string if every of the items of this subarray is a 10-character string. This is 10, this is a string, this is the shape of that field. But the whole thing is a dtype, and the whole thing can be the type of the items of an NDARRAY. We can also define, convert, the data, the keys of this type, that key, all of them can be converted to a dtype, float 64 and the rest. These two, I will explain them in more details in the next lesson, but to give you some examples, the syntax is like this: flexible item size, fixed type shape. So NP void, and the item size here, every item of that, it would be 10, and here is a 10, a string, every item of that, it would be a string with 10 characters. Here I'm saying that I want to have a data type, which is a subarray, this shape 2 by 2, by the shape of 2 by 2, and every item would be an integer, 32-bit integer. And also here I'm saying that I want to have a data type, which is a subarray of data structure. This is the data structure. The shape of that is 2 by 3, so it's a subarray, and that data structure has 3 fields and like this. I recommend you to use this style if you want to create an array of data structures. If you want to create an array of this of a data structure, you have to first create the dtype, which is the data structure. Field name, field type, field shape. So it has, for every field of the data type, you have this tuple. And inside this tuple, you have the name of that and the type, and you can also add the shape here. In this example, the first field of data structure has the name of big, the second one is little, and the type is integer, 4 bytes will be reserved, big endian and little endian. I cannot, sorry. I can also use this structure, which is names, formats, offset, titles, and item size. So the names and format keys are required. The field names must be strings. Like here, the field names everywhere should be strings. So with this one, I'm creating a data structure and the name of them and the type of them. In this one, which is this user is discouraged, you will define the field and then the type and the shape and the item size. But it is discouraged because it is ambiguous with the other DICT-based construction method. For example, here, if the field 1 is names, if you put here names, then there is ambiguity between these two. So if the name of the fields is these ones, then it would bring up ambiguities. And the last way that we can define a data type object is this one: base type and new data types. So here we have a 32-bit integer containing the fields R, G, B, and A, and they interpret, sorry, these 4 bytes integer in 4 different fields. So all of them, it's this one is an integer, but every byte of that will be considered as an on-site integer for different fields of this data structure. The attributes of dtype are these ones: type, kind, char, and the most important ones are names, shape, and description. You can work with them to learn more about them. And we also have these methods. Now I want to give you some examples. We will have many examples, but before going to the example, I want to know that if you got the theory behind data objects and scalar types and NDARRAYs. If you got that by 80%, it's enough. The 20% will be given in the examples.
Yeah, I got it. I'm just not reading because I don't see my chat.
What?
I'm not writing. I'm not typing in the chat because I don't see the chat slide, and I'm not sure why.
Okay, but you got what I said?
Yes, I got it.
Okay.
The rest.
Okay. Yeah, it might be a bit boring till now because we didn't have many examples, but we had to be like that. Otherwise, if I go to the examples, you may see, you may find many questions for yourself. But now I think you are familiar with the basic topics that we need to know. We will get familiar with other topics, but for them, then we will only learn them by the examples, not in theory. Here I'm creating NDARRAY. This is the real start of working with NumPys. With this one, I'm creating a NumPy array, and you are familiar with this function that we just discussed about that. And this is the object. I didn't define the other objects because all of the, the other input values, and I went for the defaults. If I print, and this one, the object is a list. So the input of this NP array is a list. And here, when I print that, it gives me a NumPy array. This is a NumPy array. If I see the shape of an item of this NumPy array, it gives me this because the dimension of this one is 0. It's a scalar, and the dimension is 0. If I get the type of this item, it gives me in 64. And here I'm getting the type of the array. Again, it gives me 64. Why? Because the dtype objects of the array is the type of the elements of the array. So it's not the type of the whole array. It's in fact, it's the type of the elements of the array. And if I get the type of A0, you know that we had type function in Python that we can get the type of an array. It gives me this one. It says that it's a class of NumPy in 64. And as you saw in the previous slides, we can use this function to see if one value is a scalar or not. And if I use this one, it gives me it is a scalar. type, because it's an item of this array, and we had access to that using indexing. This is indexing. I'm having access to an item of the array using indexing, and that item is a scalar. The shape of the array is a tuple and has only two, because it only has one dimension. So it has only one dimension and it has two items in that dimension. We have here, we are creating the same array, but I'm changing the type of that to a float 64. So we said that float 64 is not a dtype object, but it can be used interchangeably. I mean, it can be used instead of that, and implicitly will be converted to a dtype object. And if I use this one, then when I print A, I can see that the values are interpreted as float, even if they are integer. They are interpreted as float because we said that dtype is float. The shape of that is this one. The type of that is float 64. Now I'm creating an array of strings. With this one, I can create that. It's a list of strings. And if I print that, I can see that. If I print the shape, again, it's a one-dimensional array. And in that only dimension, we have three items. The type is detected by the interpreter itself, and it's little endian, because the default order of the way of storing the items in the memory in my machine is little endian. It's a string, and it says that it has at most 5 characters. Why? Because the crease has has 5 characters, so it is detected by the interpreter. Here I'm giving a list of lists, and I'm creating a Numpy array of that. When I print that, I can see this one. When I print A0.shape, it gives me this, because A0 is the first elements of the list, or A0 is the first row of my array. Is not an item of the array, it's a row of the array. So this row has one dimension and has 3 items inside that. If I check dtype, it says that it's in 64 because every item of that has this type. And if I check if it is a scalar, it tells me no, it is not a scalar because it's not an item of Numpy array. It's just a row of the Numpy array. I can achieve the same thing with this one, this way of indexing. This one says that all the items in that dimension. We will talk about this one later on in this slides. If I check A.shape, it says that it's 2 by 3. It has 2 rows and 3 columns, 2 dimensions. And I can update one elements of the this array by this. As you can see, the result, the A has been changed. So similar to list, we can also update Numpy arrays but they are located in the same location of memory and they have the same data types. I mean, every items of that has the same data type as the others. Till now, we only saw creating the arrays with basic data types, creating NumPy arrays with basic data types. But here we are creating arrays with data structure. Their data type is a data structure. This is we had 16 ways to create a data object. This is the 13th way to create a data object. So I'm creating a data structure. The first field name is name, and the second field has the name of age. The type of the first field is a string of 20 characters. At most, it will have 20 characters. And the type of the second field is an integer with 8 bytes. And when I'm creating here an array with this type, dtype is dt, and the list, the object that I'm sending to create an array is this one. It's a list of some tuples, and the first elements of the tuples are the names, and the seconds are these ages. When I print A, I can see this one. You see, this is a NumPy array. This is similar to have a list of tuples, but in fact, it's not a list of tuples, it's a NumPy array. If I use print A name, it will give me all the names of that. You see? So, in addition to indexing, we can also use the name of the fields in NumPy arrays if we have a NumPy array of the type of data structure. I can also use the name of the field, which is age, and it gives me these values. Here, I'm having access to A0. A0 is this one. A0 is an element of this array. So A0 is this, even if it has 2 values, it has a string and an integer value. It is only one item of the NumPy array because it is of the type of the data structure, the D type. So when I get the type of that, it will gives me NumPy void because it's a flexible data type and it can, the data structure are getting inherited from that data type. And if I check if it is a scalar, you will see that it gives you true. So it is different from the scalar values that you know from maths, or you know from Python building variables, Python building objects. An array scalar, as you said previously, it's an item of an array object, a NumPy array object, which we have access to that using indexing. How about this one? So now if I want to have access to these elements of these items, I cannot use A0, 0. I have to use this way because now we have a tuple, and to have access to first item, I can use this way of indexing. The type of that is a string, and it is a scalar. So the elements of that item also are a scalar. This is also the case with with these integer value. A.shape is 3, so it has 1 dimension, even if it has tuples inside that. You can see also here, it only has 1 dimension, and that dimension has 3 items, 3 scalar, array scalar. And dtype gives me this one. I think if here I use a0.dtype, it also gives me this one. But when you use type this, it will give you void. So it will convert it to a type that is supported with this function. Let's see this example. In this example, this is a data structure. Again, the first field is name, and the second field is the scores. The first one is similar to that one, is a string with 20 characters, but the second field is a sub-array. Why? Because it has a float, and we are saying that the shape of that is 2, so it's 1-dimensional, 2 elements. So when I create an array with these types, I have to give this. So I have Nessie with these scores, John with these scores, Chris with these scores, and the type is DT. And now when I print A, I can see this one. When I print A0, I can see this one, because the first element is this. And the type again void, and still it is true, it is a scalar, because it's 1 element of the Numpy array. And the shape of that is 3, 1-dimensional, and the type of that is this one. It is similar to what we write here, but in a different, it uses, for example, the unique codes of naming that. And let's see this one. So I have a dtype similar to the previous one, but I can also use, instead of array, this function, which is empty, to create an object, an empty object with this shape. So it has 3. I put here 3 because I didn't want to make this slide very long. I wanted to fit the whole list here, as you can see. But imagine that you want to create a list of peoples, and for every person, you want to have a data structure of their name and scores. So then you can create an empty array which has 20 elements, for example, and then update them later. So this is like initializing an array with this type, and then you can update that later. This is really a good behavior in a NumPy, because as you saw, they are stored in 1 continuous place of memory, and if you want to append 1 item to them, then it has to find for another location of memory that can fit all the items of the NumPy array there. So the access time will be higher. I mean, not the access time, the manipulating time, like immutable objects that we have, will be higher. So it is better initialize an NumPy array with the number of items that we want before updating that, instead of just appending item like what we have in list. We can also append 1 item to a NumPy array, but it's not recommended. Whenever we can initialize that like this, it's better to first initialize with empty, zeros, ones, full, and then update them later. if we know the number of items that we need. And here, if I want to update that, I can do this one and this one. As I said here, we cannot use A0, 0 because the shape of this array is this. You can see that it only has one dimension. It doesn't have two dimension. So you have to, using indexing, have access to the first element, and then to update the items of that field, we have to use another way of, again, indexing to update that, also for here. Is it clear till now?
Yeah, it is clear. I have one question, Miss. From the previous slide, when you show us that an array has two different types, it will always show us like void, right?
You will also show us what? Sorry, I didn't get.
And we have an array with two different types. I mean, for example, integer and string, as the examples you show us. When you obtain the data type, it will show us void because they are different types of variables.
Oh, you want me to explain about that one?
No, I just want to know if it will always show us void if we have different kind of types.
No, okay. Let me explain. No, we also have objects, for example. It can also show you object, but actually this is why you can see, I mean, the reason that you can see here void is because I'm using type function, which is a function of Python, not a function of Numpy. Okay, so when I use this one, it gives me, it is a Numpy void. But if I use like this one, if I write here A0.dtype, it will give me exactly like what you can see here for A.dtype. So this is because I'm using a Python function for a NumPy object. That's why I can see here, it says that because Python is replying for that. And it says that it's a numpy.void class. It's a flexible data type that can support all of these things. It's the class that Python can see. Python cannot see the details of the data structure. Okay, but if I write here A0.dtype, since dtype is a method of the NumPy library, it will give me this one, because NumPy itself knows what is inside of that. And if you are curious to know that, if you use type for other objects, if it will give you other classes instead of this one, yes, it will give you other classes, because some data types are getting inherited from the void, some other data types getting inherited from objects, but we can say that you will not be very involved in these things, because there is a wrapper for NumPy, and they will handle that inside that, and you only work with the wrapper, not the objects inside that. Did you get?
Yes, I got it now.
If you have other questions, you can ask. No? Okay. Let's see the other examples. So, in this example, I want to compare ND arrays with lists in terms of slicing. Contents of NDARRAY object can be accessed and modified by indexing or slicing, just like Python's built-in container objects. But they have some extra features. For example, here I'm creating an NDARRAY which has 4 rows and 3 columns. So with a.shape, I can have access. I can see the shape of this array. With this one, I'm slicing that NDARRAY, and it gives me an array of the item 0 till 2 and 0 till 2 again on the rows and also on the columns, and be 2 by 2. So this, if I print this one, I can see this. So the shape is still 2 by 2. I mean, it's 2 by 2. It has 2 dimensions. And for this one, I don't need to even to write the last, you know, that like slicing in the list. I don't need to write this end part if I want to refer to the end of the that array or that list. So it gives me again the same array. With this one, I'm saying that this is I want to have an array from the rows of 1 and 2, and only the second column, and it would be the shape of that. It would be 2 by 1, and you can see that it is 2 by 1. And with this one, I'm accessing again. This one. Yeah, with this one, I'm saying that all of it, these 3 dots, I'm saying that all the columns, the rows are similar to the previous one, but all the columns. So the rows are these 2, as you can see, but all the columns. But here I said that the first column, for example, and yes, from this one, and the second column, 5 and 8, I'm talking about this. And for this one, you can check them one by one, and you will see that it's very similar to Python's built-in Python's list. But they have some other things. For example, in list, you don't have that for every dimensions, because there you only have 1 dimension. But here you have multiple dimension, and you can do it for every dimension. And you can also 3 dots, which is not possible for lists. For this one, I have first a 2 by 2 array. And in 2 by 2, I can use indexing, slicing first, and indexing next, and I have access to 5. And here I'm having it with a slicing. I have one again a 2 by 2 array, and again with slicing, I can have all the rows, but 1 column of this one. So it can be done like a loop. You can do it. You can have multiple of these brackets, one after another, to do what you need: indexing, slicing, and the rest. And if I get the shape of this, that gives me again it's 2 items, and this. I'm creating the same list here, but this list only has 1 dimension, and it's just a list of lists. So I can have a slicing like this, which gives me this one, and I can have a slicing and indexing like this, which gives me this one. But this one is impossible. I cannot do this. because I mean you don't have rows and columns in list. You only have one. It's a linear object, and you have only one dimension. And also, this one is impossible in with lists. In array, NumPy array, we also have advanced indexing, which is integer indexing and Boolean indexing. Let's see here. I'm creating this NDARRAY. I think I didn't mention. I said it theoretically. When import NumPy like this, we can set a name. So this is the way that you can set a name for your library. Import NumPy as NB. So this is, you can put here, for example, Nasser. You can put your name, Rehana or GU. So anything you can put here. But NP is usually the common name that you will see in the source codes that people are using instead of NumPy. You can. It's not obligatory to set a name. You can just import NumPy, and every time instead of writing NP, you can write NumPy. But usually people use NP because it's shorter and it can be write faster. So here I'm creating another array. NDIM gives me the number of dimension that this array has. It's 2 because it has rows and columns. And with this one, I'm generating an array. Okay, it's what is this? Print NDIM, this one, and Y is. Oh, okay. Sorry, I got confused. With this one, I'm doing integer indexing, and in integer indexing, I'm using an array. NumPy array here, and you saw that we can use here a slicing, but instead of a slicing, I can also use integer indexing. I'm putting here the list of indexes that I want to have, and also for here the list of indexes that I want to this dimension. So I'm saying from this dimension I want 0, 1, and 2. From this dimension I want 0, 1, and 0. So what is happening here? From the 0, 1, 2. So 0, 1, 2. This is the rows that I have. And from the column dimension, 0 and 1 and then 0. 0 and 1 and then 0. So for the first one, okay, 0 and 1 and 2. I think it's not that one. The dimension of the first one is 1 rows, 0, 1, and 2. It's correct. Maybe I did a mistake here.
It's another, I think, another.
Yeah, I think so.
I mean, it should work with 1, 2, 3, 4, 5, 6, and from that matrix.
Here, I mean. Okay, the 2 print dimension is here. Yeah, okay, sorry. Sorry, 0 and 1 and 2 is 0 and 1 and 2, and 0 from this one is 1, and 1 from this one is 4, and 0 from this one is 5. Yeah, I have to put an enter here, then it would not be very confusing. So this is the way that you can do integer indexing for this one. For this one also, it's it's our array created here with this one. If I print that, is this one, which I was really confused with this. I thought this is that one, and I just print that one, and then rows are getting can be accessed by this one, and calls with this one. It's not the rows of this one and the columns of this one. It's the way that I'm extracting with integer indexing, and I can concatenate them here in one, sorry, it's the indexes that you can have, and I can put it here, and then X will extract those rows and columns for me in while. So if you want to go for this one, for example, I'm saying that with 0 against 0, so 0, 0 is, so this one, and 0, 2 is 0, 2 is 2, so it gives me this one, and 3, 0, so the 1, 0, 1, 2, this is and 3 is this one, and 0 is 9, so it gives me 9 here, and the rest. So it's the way that you can do integer indexing with NumPy arrays. You cannot do this with lists. Here I have again I have the same array, and I can do a slicing here, and after slicing our array is this one. And using advanced indexing for one column, I can do this one, and so I can do slicing for this one and integer indexing for this one. So you can use a mixture of integer indexing and slicing together. And we also have Boolean indexing. So if you remember in the exercise that you had, in that exercise, we had to use NDARRAY to check all the items with non-object to get the IDs of that location. I mean, to get them. But we can also do it with Boolean indexing in NumPy array. But first, let's see how we can solve it with what Boolean indexings are. So again, I'm creating the same array, and this is the array that we have. And the items that are greater than 5 can be accessed using this one. So with this one, I have the items of that are greater than this one. So it gives me a one-dimensional array with the items which are greater than 5. I can also use other Boolean functions here, like this one is NumPy is complex. So if this doesn't mean that the whole item is if it is a complex, it means that if the items of I mean, it will run that function for every item of that array, and then you will have this one. So it will gives you the items that are complex. So this is the example, the exercise that you had, and we solved it with these 3 ways. And the best way we said that is this one with enumerate. We can do something like this, but this one, I mean, I just did this exercise before the class, so it's not exactly what we wanted in this exercise. We wanted to have the position of this none, but with this one, with this array indexing, I have Boolean indexing, I have the items itself. So it's somewhat different, but we can have this one in array in NumPy arrays, but we can't have this one in lists. So we have a list here similar to that one. I can create an array from this one, even if the items are, the type of the items are different from each other. And when I print this one, I can see this is similar to a list of that, but it's an array of that. dtype, if I get the dtype of that, I can see it's the interpreter detected it's as an object, so it's just an object. So we can say that the base class that the NumPy is using to have all these different data types as one dtype object is object. So if you remember, we had a scalar type named object underline something, and at that time I told you that you should remember this in your mind. Sometimes if you want to have different data types in one array, you can go for object, and if you don't need even to define that, it will be, if you feed array object with a list of different data types, it will detect the type as an object like this. And so the shape of that, it has 8 elements like this one, and I can have access to these elements with this one. So it has one dimension. So if I want to have the access to that, I have to use this one. For example, A7, and have access to this member, I have to use indexing after the first indexing. And also for this one, the same. I mean, the first element and the second element. And if I want to have access to, I think there is a mistake here again, 0, hello, this one is hello 2, and this one is 87, A70, A7 is this one, and 0 is this one. Why we don't have 2 of this here? Maybe I didn't. Okay, but this one is this one is this one. No, is this one? I think it's the order is different. Maybe I didn't run it again, and this is the previous run of my code. But let's check one by one. A is this one, dtype object is this one, A70 is 2. Okay, A70 is 2. No, again this. So I have to correct this slide, I guess. Yeah, I have to correct the results here. But if I want to have access to the elements of none, I can have them like this. I can just write this and none and have access to that. This is Boolean indexing. I don't know if we can cover other topics. Let's see what we have. Copies and views. We can talk about copies and views, and it's 3 slides. I think you will be tired, and I am also tired. So we can finalize, I mean, we can stop the course today by this, and then I will, let me make it. Okay, so you can, till now, you are familiar with NDARRAYs, how you can create them, how can you access to the items, how can you use slicing, indexing, advanced indexing for your NDARRAYs. But you need to know, for example, the topics about copies and views, how we can reference the variables to each other. You need to know about views, which is a new topic that you don't have on the list. You need to know or to compare them. This one was also about comparing lists and arrays. And then you need to know about reshape and arrange, which are similar to the range iterable object that we have in Python, but it's different. And how to traverse on NDARRAYs, how to broadcast them. I mean, one of the examples that that I had when I was talking about Numpy was about doing mathematical operations between the arrays and scalars. So this is the topic that we have to discuss about that in the next lesson, broadcasting. And this is how we can do broadcasting. And there are some other functions that we will discuss next lessons. But I think since we gave much theory today, it's better to stop teaching today. I guess you will be we will get confused if you have too much information in one lesson. So if you will attend the next lesson, I will give you these things. But it would be great if you want to attend the lesson to let me know, for example, by the end of the week, because I don't have the slides now, and because of this course, I'm creating the slides, and so if you don't attend, then I will create some slides. I have to spend time on that, but then it would be like wasting time. Not exactly wasting time because I'm also learning, but it would be great if I know that in advance, that if you will attend the class or not. So if there is any question, you can ask. Otherwise, we can stop the lesson today and discuss about the rest of Numpy. I think we will discuss also about, if we have enough time, next in the next lesson we will talk about classes, functions. We still have 3 more lessons. We gave 3 lessons now, and in total we have 6 lessons. I mean, we have good progress till now. We have we know many things, but there are some other things left that we should learn. So if there is any question, you can ask. Otherwise, we can leave the meeting. No questions?
No questions for me. You asked me.
And Gio, I should tell you that I really didn't have time to check your homework. I will check that for sure by the end of the week. But I really was busy with my other research topics and also the slides.
Yes, no problem. No problem.
Okay. Rehane, don't you have any question? Is everything okay? I'm not sure if she's listening to us.
Yes, me too.
Okay, so we can leave the meeting. Have a nice day to you, and I hope it is useful. And I really suggest you to do the examples, to implement the examples by yourself. And if you have any questions about the examples, you can manipulate the Numpy arrays and the list and check them with their IDs and the rest of the thing. I will do that in the next lesson, but if you do it by yourself, you will learn much better than just having the class in theory. So you may think that you understand what I said to you because I gave the examples to you, but if you implement yourself, you will learn it much better. So have a nice day. I hope it was useful to you. And if you want to come to the class for the next lesson, please let me know by Friday evening.
Through the mail?
Yes, through the emails. It would be great.
Okay.
But my etro will be email.
Yes, the last one that you sent us.
Yes, exactly. Okay, have a nice day.
Thank you. You too. Have a great day.
Right, thanks. Bye.
Bye-bye.